workshop that is looking at the challenges, new challenges and new things in robotics and automation. What I did is just have a look in the area we are working in medical robotics, how the problems appear compared to the more classical robotics in industry. So the main thing here is the fact of human and robot interaction that in the medical field is very, very intense in different ways. So we will see because there is the interaction with the patient, interaction with the clinicians, etc. There is a different kind of interaction, physical, cognitive, of control, etc. So we are working in the different areas of medical robotics, that is assistance, that is rehabilitation and surgery. In all these aspects have something in common and of course also some big differences. For example, in assistance, we have to deal with an external robot being an assistant arm that assists people in daily living, or other kind of robots like wheelchairs or a smart walker that assist a user, elder or so, to just go around. In rehabilitation, the interaction is much closer because there is quite complete physical, mainly in this kind of exoskeletons of physical contact of the human and the robot, which goal is that they cooperate. It's a cooperative task because we expect that the robot doesn't do everything. The main goal of rehabilitation is assist the patient as much as needed, and not more than that, because on the contrary, it produces slack. So the human relax when someone has to work for him or her. It needs the interest or the action to relax. So we have to just do what is needed. We talk about exoskeletons, treadmills, or combination of all of these with support for weight compensation, etc. All the things that exist in cooperation. In surgery, there are different problems, of course. For example, in this case, we show here robotics or laparoscopic surgery. Here, the interaction is directly physical, the robot with the patient, or the instruments with the patient, but also the surgeon that is controlling the robot for the task. So there are two different kind of interactions. So in this case, what shown here is a lab scenario of the slave robot doing this laparoscopic task celebrated from the surgeon. So we'll focus in the robot control aspects that we have to deal that are different from the more classical problems in robotics. Just giving rough ideas is one is positioning, the other is because many tasks is just position the robot at some point. Others have to follow a trajectory, so trajectory evidence is the cue. And in other cases when we have contact with objects or with humans, there is the concept of force control. In the first positioning, it's clear that in industry we have very, let's say, easy situation because everything is pre-established. We have the sensors and the actuators that, in this case, locate the car structure in a given point, so the robot has just to go to that point in a predefined way. If we focus on the other applications we have mentioned in assistance, we have to deal with the user of this application, that in some cases, in this case, the robot is approaching something. In most cases, the user can facilitate the task because he can approach the robot, but in other cases, it is not the situation. The disability may impede the user or even move meanwhile, so the robot has to adapt to the specific positions and situation of the patient. In this case of rehabilitation, we have here a user in the treadmill. In this case, is a, let's say, robotized treadmill that adapts the speed to the possible to the velocity to advancing the speed of the user. So we have to detect precisely and continuously adapt to this capability of the user. What is the problem of positioning in surgery? There are some applications in which we can predefine the position of the patient, like the applications in which stereotaxis, for example, in brain, the head interventions, we can fix the position. So once we have established and we have calibrated the system, we know always where the patient is. But in many other situations, like in this case, okay, so the axis, I don't know why animation doesn't work. The axis, in this case the leg, we cannot fix the position, or if we can, is some invasive action fixing the position of the arm of the leg. So as much as possible it has to be avoided because it has shown to have clinical consequences later on. So there's still problems, or there's still challenges in robotics to continuously and on real time to position to know, to detect the position and orientation of the patient to be able to perform it. So we cannot. So when one refers to trajectory reduction, again, it's the same thing. Referring to industry, coming back to welding actions, before was point-to-point welding, now is arc welding that needs a trajectory. In this case, either because the trajectory is quite established, or we have perception systems or vision to detect the joint that has to be well, and it is clearly defined. But on the contrary, in other applications, for example, in this example, we have a user. The user we combine different enterprises. The volitional order given by the brain launches a pattern action done by the robot has to assist the user to do. But of course, we cannot oblige the robot or oblige the person to do exactly this trajectory. We have to rely on the patient as possible contribute, or at least that the movement is compatible with the status of the patient, of the rigidity, the stiffness of the muscles at the time. So we cannot force this trajectory in any way. The same happens in a walking process. The control of exoskeletons is based on the pattern of the human gait, but everyone, due to the different sizes or even due to the different status, the spasticity, etc., may change not only from one person to another, but continuously for the same person. So the exoskeleton, the difference as in human and robots, has to continuously adapt to the status and that are like perturbations in this trajectory. In the case of surgery, it's the same again. There are many of the routinely tasks, for example, surgeons complain that the advances of robotics are slow, and they do very routinely tasks continuously, and they say why the robot cannot do that. But of course, the size, the form of the card, of how the insertion has to be done, the state of damage of the tissues, etc., that forces that some intelligence is there to do that. So there are a lot of work to try to fix parameters, to fix the things needed that this routinary task can be adapted to the specific situation at every time. And the other is for force control, where we are in contact, again, in industry or in service. We have a force control to do some tasks as here at drilling. And in the case of assistance, we have here a robot shaving. Shaving robot. The shaving robot that is adapting to the position, and in this case, even the human can adapt. So we have to establish a strategy. For example, in this case, the strategy was to be perpendicular to move perpendicular doing this actions perpendicular to the face of the patient can adapt and do this. The same in rehabilitation. In this case, we see rehabilitation not with an exoskeleton, but with an system arm. That in this case, the therapist shows a trajectory, and by force control, we memorize this trajectory that has to be then repeated again and again. Of course, adapting all the necessary corrections that due to the patient status may occur. The same for the exoskeleton. This is a project, type of project that we're working on. That the exoskeleton is applying this. In this case, the user is doing nothing. It's just the robot doing the action of walking. And so the work now is how to combine this in order that the patient with different situations can so that we don't force this exact trajectory that may produce damage to the patient and so on. So we'll mention a little bit of that. In the case of surgery, also there are a lot of applications. We have the operation. There are some tasks that can be done autonomously, provided that the robot can be fixed and the position can be quite established. But there are other situations in what is convenient is this cooperation in co-manipulation, the human and the robot. And in that case, we see that the human is doing really the task of movement relief. But as we see beside in this screen, we have generated a virtual picture that helps the surgeon to move towards the point of interest, to impede the robot to reach a specific point that can be dangerous, like touching an nerve or something that can produce damage, paralysis in the case of the medulla, etc., etc. So the problem we have to face is that we have to adjust trajectories positioning in space, in time, as we have been mentioned before this morning. We have to adjust in shape, for example, in surgery, all the organs are this, or in rehabilitation, and the shape of the patient is different, and also to the patient status, and that in any situation the patient can contribute more or less to what's happening. So if we are thinking in a system, for example, in the rehabilitation field, thinking that a person has to control their arm orthesis or their arm prosthesis, just volitional through mental orders. One of the things we find that the orders are quite difficult to interpret. Here we distinguish between two real states, relaxed or in a volitional state. So basically, up to now, the order's brain control is just to start some pattern, not just to control the pattern, that we are still far away from it. But anyhow, in this case, we have still a lot of doubts, a lot of uncertainness in interpreting orders. So these orders can be uncertain, and so we have to evaluate if the interpretation done is good or not. So for that, it's interesting to analyze the environmental circumstances. So we have to see if what this interpretation that is not very robust we have interpreted, we have to compare and see if it is feasible within the external conditions or even the status of the patient or even on the sequence of the actions. So there are many other inputs that together with the order will decide what to do. So and this will correct if necessary. From this information, once it is certain, we can say, okay, we start this pattern of walking or reaching an object, etc., typical actions for a system in daily life. But of course, and this is what we have in a database, how is the pressure of reaching, how is the pressure of walking, etc. But in any case, we will have to redefine this trajectory according to the status of the patient and according to these things. And this means that here something happens. It's not the typical control input, output, or input and output and correct PID algorithm and so. So for example, we see here, if these are for a given task, for example, the trajectories that each of the joints have to do, and these visualize the constraints, that focus angularities and the environment conditions, the points that each blue with blue, red with red, that each joint cannot reach, then we expect that the trajectory is deep. But when we try to execute, we will have to correct for some reasons. For example, one thing is that the user cannot go as the necessary or as the established speed. So what we see here is that the trajectory with respect to the previous one has enlarged in time. But what is important? To do exactly what we expect or not. So in that case, that is not the point-to-point control that we have to do, but analyze the trajectories over time. And the other thing is, if there is a delay, and we have to expect, not forced to do, maybe the user needs some time, or maybe we have a collision, and so because the user cannot act with one of the jobs. So we may have to know these things, the pattern of walking, we have to control, for example, as I said, we may have for each of the jobs a strategy, but we just mentioned that we have to accelerate and accelerate. And in surgery, we have to adapt to moving parts. In this case, for example, we are working on how to compensate the hurt movement. So for operation on orthopedic hair, that means that we have to understand or to follow or to see the deformation of the head while it is beating. And what we see here is a robot that is still operated. The second robot is just following the same movement, and so this stabilizes the image, and the robot can track. So this is what we have here. We use also this for these studies on object deformation. For another of the challenges we have in surgical robotics, that is estimating force, as we cannot have force sensors on the tips of the instruments. We have to estimate in a different way if we really want to feedback the force of the user. So in that case, we are combining what the sensor, force sensor detects as force, and how the force, in order to infer from vision the force applied and show understand. And finally, this example of positioning at the beginning of the intervention is quite important that the patient is located in the right position with respect to the robot in order to assure that the robot is able to reach all these points or space. So it is important to facilitate the information previously to the patient. So we are working with this interface for this interaction. So we will compute previously for a given situation how it will reach. The surgeon can say, okay, I have to operate this way or this other, move the patient and so on. And so there are many challenges. And just to finish the conclusions, the thing is that the human is in the loop. This is the common sentence in the education. That this implies that unpredictability and special needs of safety. In this case, we have the patient, user, that changes in shape, size, status, movement, the will to do something, and the specialist that give orders, that define the task, that has to solve incidences. So there is a continuous adaptation to changing conditions and uncertainties. And in the other sense, we have, for solution of these problems, we have sensing and perception. To interpret this, we need learning for multiple trial and demonstration. How is the trajectory, how is the variations we can expect from there. Be aware of the context, context awareness to really correct these things and deal with uncertain heterogeneous data signals that's appear. because you always wonder how to do some trajectory and sometimes how the physical way of the robot. Of course, for each application we need robots because for each intervention, I was mainly for many different kinds of interventions, different robots to design.
Okay, just to phrase it, you have an aerial robot, so it can go anywhere. You know, I mean, is there any other thing that would be this? Everyone.
Yeah, of course, we have to be quite imaginative because when you work with solutions and so sometimes you think, okay, we have a robot and we will program something very complex, very intelligent, and then the problem is anything and you have to invent mechanisms, devices, and sometimes it's true that we have big robots and for many applications, maybe it would be better to think how, because we don't think of robots to substitute solutions. We want the robots that assist in specific things mainly, and one is important. This is what I think. Our goal is not to move apart the solutions that assist. And sometimes the systems, maybe the instrument, maybe another thing. And it is a big, and this sense there is a big debate on how much we need robots for this kind of task.
So maybe a quick follow-up then. It seems like a lot of the parts of this, because I agree with your overall big picture background, but the trajectory generation and ensuring that constraints are satisfied, right? So what's your insight in that generation process? For example, exoskeleton, you have dynamic stability. If you're going to achieve this, you need some sort of model between the system. I mean, it gets very complicated very quickly.
Yeah, it's just an idea, and it's true that their problems came from different things, different ways.
So what's your insight in the I guess future of generating these trajectories and the role they'll play?
Well, the steps are very, very, very slow because every time you do something, you find new problems. In this case, it's to generate, let's say, it's learn and to see the variability of this kind of trajectory and try to continually to combine with many, many variables coming from the patient and coming from the action. So we need the sequence of actions that this implies, identifying which of the steps and what are the external conditions for that. So how we know system steps. This is just a simplified view, just to